MAXVY.
Welcome to the part 3 of MAXVY's Verilog tutorial series. In this video, we will continue to see the remaining topics in the hierarchical modeling concepts. In this video, we will discuss the importance of modules and instances in our design process. Finally, we will cover the components of simulation, focusing on the design and simulation blocks. Modules. Modules are the unit building blocks of Verilog used to describe an entire hardware system. A Verilog module is enclosed between the keywords module and in-module. It has the following components. Module. This keyword initiates the definition of a Verilog module. Identifier. This is the name you give to your module, which should be followed by the standard naming conventions for Verilog identifiers. And then the list of puts. These are all the inputs and outputs of your module. They define how the module interacts with other modules in your design. Then the optional list of parameters. Verilog allows you to define parameters for your module. These are the constant values that can be customized when instantiating the module. And then we have the list of port declarations. Ports are declared with their direction, like unidirection for input and output and bidirection for in-out ports. And it also declared with their data type, like wire, reg, etc. And then the module items. This encompasses the actual Verilog code that defines the functionality of the module. It can include assignments, always block, and other Verilog constructs. Finally, this keyword signifies the end of the module definition, which is end module. In this slide, we will discuss how to instantiate a Verilog module. Instantiating module is crucial for creating complex designs by reusing smaller manageable modules. A Verilog module can instantiate other Verilog modules. This creates a hierarchy of modules, forming the full design and test bench. Any module that is not instantiated is considered to be at the top level. The Verilog module instantiation statement allows creating one or more instances of a defined module. This facilitates using the same module multiple times within a design. You can create multiple instances on the same line and specify a range to create an array of instances. Here is the basic syntax for instantiating a Verilog module. You can start with the module name, followed by the instance name, and then the port connections. This structure is straightforward and allows for clear, organized code. In this slide, we will explore how to connect ports in Verilog. There are two primary methods to connect the ports, by position and by name. Connecting by position means connecting ports in the order they are listed in the module declaration. Connecting by names involves explicitly naming each port when connecting it, providing greater clarity and reducing the risk of errors. Here, we define a simple module called AND gate. It has two inputs, A and B, and one output, Y. The output Y is assigned the result of the logical AND operation between A and B. This is a straightforward example to illustrate module definition. In the top module, we declare wires A1, B1, Y1, and A2, B2, Y2 to connect our instances. These wires will be used to connect the inputs and outputs of the AND gate instances. This line shows the positional instantiation of the AND gate module. The instance is named U1 and connects the inputs and output in the order that they were declared. Here, A1, B1, and Y1 are connected to the respective ports of AND gate. This segment demonstrates named instantiation of the AND gate module. Each port is explicitly named and connected, providing clear and readable code. The instance U1 connects A to A1, B to B1, and Y to Y1. This method is particularly useful in complex designs with many ports. Verilog code for ripple carry counter. Let's start by looking at the top level module of our design, which is the ripple carry counter. The top level module integrates all the components needed to create the counter and defines the overall functionality. This module is named ripple carry counter and it has three main ports: clock, reset, and Q. The clock is the clock input that drives the counter. Reset is used to initialize or reset the counter to 0, and the Q is the 4-bit output that represents the current count value of the counter. Within this module, we have instantiated 4 T flip-flop modules, which are toggle flip-flops. Each T flip-flop module represents a single bit of the counter. The first T flip-flop instance, TFF0, is directly connected to the clock signal. The output of TFF0, which is Q of 0, drives the clock input of the second T flip-flop instance, TFF1. Similarly, the output of TFF1, Q of 1, drives the clock input of the third T flip-flop instance, TFF2. Finally, the output of TFF2, Q of 2, drives the clock input of the fourth T flip-flop instance, TFF3. This chaining effect means that each T flip-flop toggles the next one in sequence, creating a ripple effect. When the clock signal pulses, TFF0 toggles its states, and this change propagates through the chain of the T flip-flop modules. This results in a binary count being stored in 4-bit output Q. Now let's delve into the lower level block of our ripple carry counter, the T flip-flop module or T flip-flop. This module is crucial as it is provide the basic toggling functionality required by the counter. The T flip-flop module has three ports: clock, reset, and Q. Inside the T flip-flop module, we declare a wire D, which will be used as an intermediate signal. We instantiate a D flip-flop named DFF0 inside the T flip-flop module. The D flip-flop DFFO has its output connected to Q, its clock input connected to clock, and its reset input connected to reset. The data input of the D flip-flop DFF0 is connected to the wire D. A NOT gate named N1 is used to invert the output Q. The output of the NOT gate, which is D, is then fed back into the data input of the D flip-flop. This feedback loop causes the D flip-flop to toggle its output state on each clock pulse, effectively making the D flip-flop behave as a T flip-flop. Now let's look at the variant of the D flip-flop module or D flip-flop, which operates on the falling edge of the clock and reset signals. D flip-flop module has four ports: clock, reset, D, and Q. The core functionality of the D flip-flop is defined within an always block. This always block is triggered on the falling edge of the clock signal or the falling edge of the reset signal. When the reset signal is active, low, the output Q is set to 0. When the reset signal is inactive, on the falling edge of the clock signal, the data input D is sampled and assigned to the output Q. This means that the value of Q updates to the value of D at each negative clock edge, provided reset is not active. In this slide, we are going to see about the parts of simulation. The stimulus block generates the inputs that will be applied to the design block. It also provides the necessary stimuli to test all the aspects of the design under various conditions. This is the actual module or circuit that is being tested. The design block receives the input from the stimulus block and processes them according to its logic. The design block's purpose is to stimulate the real-world functionality of the hardware or logic being designed. Example of design and stimulus block. Here you can see the basic design block of an data flip-flop. The data flip-flop latches the data input D on the positive edge of the clock signal and outputs this data on Q. Here we define the D flip-flop module as DFF with inputs clock and D and output Q. Inside an always block triggered by the positive edge of the clock, we assign the value of D to Q. In the case of a stimulus block, the test bench generates the test signals for the D flip-flop. It initializes the clock and data inputs and applies different test vectors to test the D flip-flop. Here we declare clock and D as register because they will be driven by the test bench. We instantiate the D flip-flop module, DFF, and connected ports to the test bench signals. We use an initial block to initialize the clock to 0 and toggle it every 5 time units to generate a clock signal. Another initial block applies different values to the data input D at specified times to test the D flip-flop's behavior. Do you have any questions or doubts? Feel free to write your comments and doubts in the comment section. Thank you. See you in the next video.